I'll even feed you lunch. You could be even 30 minutes late if you want to. Get those jobs before we go back into recession. Okay. Yeah, so there is quite a few. I mean, you might have gone around, but there is a lot of people who are hiring even at undergraduate level. So what we did last, a few of administrative things. There is a software lab next week. Hopefully everybody has survived the lab 2. And then we have a homework 3 due today and homework 4 due next Thursday. And then one more homework and then we'll ease off for a little bit on you. I'll give you a project to deal with instead, midterm and then a project. But there'll be homeworks too still, but not like this every week. Any questions about this? Everybody knows what is lab 3? Continual learning cadence. So after lab 2 and lab 3, you can basically, you have functional working knowledge of the program. And we'll have 2 more labs to simply strengthen that. Okay? What did we do? In the last lecture, we studied the MOS transistor and basically developed its model. From now on, I really, throughout most of this class, I'm not going to care too much about the physics of operation of a transistor. All what we're going to rely on is this model. Sometimes we'll have to understand the limitations of the model. And then I'll try to say, remember that from the physics of the operation? Well, we did model that exactly correctly. But that's basically it. Today, I'll show how to use that model in the simplest possible example, static voltage transfer characteristic of an inverter. And then after that, I'll talk a little bit more about the physics of the operation of the transistor last time when I introduced how MOS capacitors look like. Any questions about the material? Quick recap. How did unified model look like? ID was equal to either 0 if VT was VT was greater than VGS, or K prime W over L VGS minus VT times V effective, VD effective, minus VD effective squared divided by 2, correct? Where this V effective, this is for VT, VGS greater than VT, where this VD effective is equal to the minimum of VGS minus VT, VDS, and VD-SAT. And this VD-SAT is a given quantity. Is this something that is easy to remember? Yes, okay. What is the main advantage of this model? Easy to remember. A few other advantages. It's relatively accurate. It's fairly accurate. You can fit it to a real curve, IV curve that comes out, measured out of a real transistor. But it's easy to remember. What are its disadvantages? Doesn't take into account that's too hard of a science for this level. What is its main weakness, primary weakness? Why you cannot put this in SPICE? We can add 1 plus lambda VDS. That's given. That's easy. That's fair enough. You can add in any of the regions here times 1 plus lambda VDS. That's okay. Thank you. But I said it's reasonably accurate. I mean, it's accurate for us. If you feed it to SPICE, it should give us the same results, right? Yeah, that's a good observation. So that he said almost the right thing, except that it's not discontinuity. The curve is continuous. The curve is continuous, but is not differentiable. It's not smooth. It's okay for hand analysis. You guys know how to handle that. Got it? Right. I mean, what I just said, when you plot VDS versus ID versus VDS, you have the behavior that looks like that, and we abruptly say, oh, now it saturates. Here, oh, now it saturates. These points are not smooth. That's fine for hand analysis. And most of our circuits, we are going to find out, don't operate in that region, so it's okay. And by the way, yes, that's where the weak, in many cases, weak inversion you're going to encounter, and the model is going to be awful there. Okay? Yes? Yeah, if it is a long channel device, VD-SAT is always greater than VGS minus VT, and you're good. It will be smooth. Then it's fine. That's the Sherman-Hodges equation. Mass level 2. Yeah, long channel. VD-SAT is greater than VGS minus VT. Okay, is this clear? Usually you should be able to intuitively test what is the region of operation of a transistor. But this gives you a very simple shortcut to do that. If I give you a VDS and VGS of a transistor, could you tell me how would you figure out what is in which region of operation is it? By comparing VGS minus VT, VDS, and VD-SAT. Which region of operation is it if VGS minus VT turns out to be the smallest? It will be saturation. What if VD-SAT turns out to be the smallest number? Velocity saturation. And what if VDS turns out to be the smallest? Linear. Easy. Now, just keep one thing in mind. Short channel devices, really don't have that saturation. Everything is velocity saturated. We did it for the modeling reasons. Otherwise, we would have had a badly discontinuous model. Can you repeat it for me? The whole thing about how the velocity saturation in short channel device, all devices, short channel devices are always velocity saturated. There is not that thing that is saturation. But we introduce that region to have easier modeling, so we don't have discontinuities in the model. And the difference between velocity saturation and saturation for a low VGS short channel device is negligible, because the difference between VD sat and VGS minus VT is negligible. It's very small. Make sense? And we ended up with a nice continuous model. Why don't we use this model in 140? I mean, in 140, whoever has anybody taken 140? I'm pretty sure I've seen a few of you there. You would like to volunteer an answer before I harass Nick? Yes, exactly. And badly behaved derivatives are really not good in 140. So we stick with something that is more smooth over there. Make sense? There are smooth models that are accurate, and I've shown them in the last lecture. Why don't I use that one? Hard to remember. But those of you who take 241 will use that one all the time. We'll throw this one out, and then you become graduate students, and you're required to remember a little bit more complex model. Okay? Or you're treated as graduate students. Make sense? Because not everybody is, assuming that not everybody here will be designing chips in this classroom. But if you go for 241, I'm assuming that you're determined. You haven't had enough of it. You're going to go design chips. Okay. Any questions? Now let's put this to use. I would like to analytically find what is the voltage transfer characteristic of an inverter. Right, what is the voltage transfer characteristic? I would like to draw the thing that we have talked about before, V in versus V out. How I'm going to go about that? Sorry for tearing up your ears. So how is that going to work? How am I going to do that? How am I going to go about that? I've found out how do I do ID versus VGS or VDS? How do I find V out versus V in here? The only thing that I know so far is ID versus VDS, VGS. Yeah? Yeah, that sounds logical, right? So, my V out here is essentially equal to the VDS of the NMOS transistor. Simultaneously, V out is equal to the, how about with respect to VDS PMOS of the PMOS transistor? It's equal to the VDD minus V source drain. And what is V in? Equal to the VGS of the NMOS, but is also equal to VDD minus VSG of the PMOS. Okay, so at least for the NMOS transistor, this is straightforward, right? V out and V in are clearly related via IDS. I just need to plug in probably the IDS of the PMOS. Solve KCL and be done with it. Okay. So here is how we do that. This is the exact same thing as we have done. I need to somehow put in order to plot this whole thing, I would like to plot the PMOS transistor in the same coordinate space. So I'll take my V out, which is equal to VDS in, versus IDN. How do I plot the PMOS curve? So my IV curves of the NMOS transistor look like, I can draw it in, say, red. NMOS transistor looks something like that, okay? Now PMOS transistor in the same coordinate origin. IDP, if counted as drain to source current, is going to be negative. We would like to look at ISD. Then it's going to be positive in the same coordinate origin. So it's going to be the same thing as ISDP. What is VDS of the PMOS transistor? Well, V out is equal to VDD minus VSD. Okay, so it's equal to, here would be a coordinate origin, and these curves would go like that. Okay, and this is what essentially we have done here. We have taken ID versus VDS curves, which are supposed to be exact mirror images, reflected mirror images, symmetrical with respect to the coordinate origin. To the NMOS ones, we have substituted the axi IDP with IDN, and then shifted the whole thing to the right by the amount of VDD, and got the same curve. Everybody clear how we drew this in there? So what is now, if you trust this model, this what I've drawn in here, what is going to happen as I increase V in? Where is my V in here? VGS, right? So it is going to be equal to VGS. And where is VGS here? It's the parameter here. So this is with increasing VGS. So as I'm increasing VGS, I'm going to start picking one of these curves. What's going to happen there? We're going to look where the intersection is. So we'll have to find out, okay, now if I know what is this VGS, what do the green curves correspond to? These curves are going down with V in, right? Because VSG of the PMOS transistor is equal to VDD minus V in. As V in goes up, VSG goes down. We'll need to find matching curves. So, for example, this one, low VGS curve here, red one, will have to match up with a high PMOS curve, medium one with a medium one, high one with a low one. And I'm going to start looking for intersections between them. And here is how it looks like. So when V in is 0, what is the solution here? You know, all NMOS curves are laying along, you know, that corresponds to the x-axis. The current is 0 when V in is less than VT. And it intersects with the top curve that corresponds with the PMOS transistor, where V in is equal to 0, where VGS is equal to VDD, the maximum curve. VGS absolute value, okay? So the intersection is right there. When the transistor turns on, say, 0.5 volts, that is like 50 millivolts more than the threshold, NMOS curve is this low one and intersects with the PMOS curve that corresponds to V in of 0.5 volts, which corresponds to the VGS of 2 volts. So there is some intersection here. Next one is V in for 1 volt, corresponds to the curve of V for PMOS for V in of 1 volts, moves up there, moves like that, moves like that, moves like that. Okay. So for each value of the input, I've found what are the currents, but I don't care about the currents. I would like to find out what are the output voltages. Where do I find out where the output voltages are? They're right here. The values here. So going back. So when V in is 0 volts, V out is 2.5 volts. When V in is 0.5 volts, it's a little bit less than 2.5 volts. I'd say 2.4 something. When V in is 1 volt, it's like 2 and a change. When it's 1.5 volts, whoa, it's all the way down. So it has passed the switching. It went through this high gain region and went down to about a half a volt and continued going down. So what I've sketched here is something that looks like this, right? I mean, this is flat 0 up to the threshold, and then at, you know, it reaches about 0.5 volts. This drops down to 2.45, then drops down a little bit more, then drops down. You know, what we find out here is that we have not been plotting this with that much of a resolution, so we don't know exactly what's happening in here. Is it a line like that, or it is even more curved? Well, that's the gain of the inverter, essentially. Anybody knows how to reproduce this kind of plotting of the VTC? How would we go about doing this analytically then? Can I analytically plot this whole thing? Yeah, exactly. It will be a little bit painful, but it's, you know, very doable. In order to do that, we would need to identify regions of operation, because we don't have just one equation, right? We have these several equations that govern the operation of the MOS transistor. So when V in is 0 and the output is high, regions of operations are as follows. We know that the NMOS transistor is off. PMOS transistor is in which region of operation? It has its resistive or linear. Why is it in linear region when NMOS is off? It's high VGS. It's, you know, ready to conduct stuff. It's just there is no current to conduct. As soon as there is some current, it'll let it go. So although PMOS transistor also has a zero current, we'll call it to be in a resistive region, because as soon as the NMOS transistor starts conducting current, PMOS transistor will be resistive. Now what is going to happen here is when NMOS VGS becomes large enough, this voltage starts dropping down. When NMOS starts conducting over here, when it's around these points, in which region of operation is NMOS? It's saturation, or maybe velocity saturation. Well, here is, would be saturation according to our model. Here it gets into velocity saturation. You have to check that. And then as it goes through, it's definitely velocity saturated, and eventually will become linear again. And here what we will find out typically, this is velocity saturation. PMOS may be saturated or maybe velocity saturated. Then eventually PMOS is going to enter saturation. NMOS is going to be resistive. NMOS resistive, PMOS off. Now there are some important points in this curve that I would like to calculate. What are the points that I care about? I would like to find out what is the switching threshold, what is this value here. Do I find the noise margins as well? Sure. Okay, let's do that. Let's find out what is the switching threshold here. How would I analytically find the switching threshold? I'll need to find the regions of operation to do that. Yeah. What we need to do, we are pretty sure that if it is an inverter and it looks like this, so what happens here when we have a switching threshold? V in has to be equal to V out. And we know that IDN, say IDSN, has to be equal to ISDP, right? Or minus IDP, which is also equal to minus IDP. Notice that Bock prefers this minus in front of IDP. I'm having difficulties dealing with negative numbers. I like positive numbers. And I try to keep my numbers positive. So I will often use ISD. Different people have different preferences. Yes? You're also having problems with negative numbers. I skipped that when I was in second grade or something like that when we did that. Both of them are on, right? We expect them to be both on over here, right? And the current has nowhere else to go. Yes. Yes. Well, but what we have here, V in has to be equal to V out in order to find to satisfy the switching threshold story. Yes. Yes. Yeah. Holds for any of these points. So you're basically equating two equations to solve this. You're solving a set of two equations. The one says IDN is equal to IDP, which is this curve. V in equals to V out is this straight line. We're looking for the intersection of the two. ID is equal to 0 is equal to ID of 0. That makes sense to me. 0 is equal to 0 still. Positive number, I do not make, or actually it's not a non-negative number. I do not make mistakes with those. Fair enough? We are essentially solving a set of two equations. Currents equal, govern the behavior of this curve. V in equals to V out governs the behavior of that curve. What's the solution? How do we go about that? How many variables do we have in there? A set of two equations. If you have only one variable, that would not be good. We'll have too many solutions. Or no, or impossible. We would have 0 solutions. So we better have two variables there. So ID is a function of VGS and VDS. VGS and VDS are related through VDD minus the other one. Therefore, we essentially have two unknowns. And this whole thing can be solved easily. Okay. So the way how we go about that is this is IDN. This here is minus IDP. We have to satisfy the KCL. These are well-known equations under the assumption that the both transistors stay in velocity saturation in there. We'll have to verify this. Every time we do a problem, you'll make an assumption about the operating region because it will look obvious that it is in velocity saturation. But you have to verify it, whether it is really in velocity saturation in the end. How are you going to verify that? We'll find out what is VGS, what is VDS, and cross-check against VDSAT. VDSAT has to be the smallest one of the three. I basically have, when I equated these two equations, I just have one variable, which is VM. I solve this for VM. And I get this relatively hairy expression, which is not that hairy. It tells me something interesting. The only parameter that is under the designer's control here is the sizing of transistors. Now, in digital world, we will very often, for now, before I add more trouble to your lives, we'll deal with minimum or with shortest channel length devices. Shortest channel lengths. Why? Because those are the fastest transistors, and we like faster chips. Later, we'll talk a little bit about why not always do that, and you'll find out that and that was true until 3 or 4 years ago. But Intel's microprocessors now don't use minimum channel length devices. By the way, why is that? Unless very sparingly they'll use minimum channel lengths. Why is that? Intel or AMD or whoever you like. Very sparingly, very few short channel devices will be used. Small percentage. I mean, still millions of them, but small percentage. Why? It's leakage. Because short channel length devices tend to leak. They do not like their chips to leak too much. But while the leakage was not that big of an issue, go for it. Use all minimum channel length. Okay. So what you find out what is under designer's control is a ratio of WP over WN, which says that I can, by doing this, I can change the shape of the VTC. I can change the switching point by changing the ratio of WP over WN. Well, anyway, I made a mess over here. This was supposed to stay there. But see what I can do. You know, if I change WP over WN by a lot, I can change the switching threshold from 800 millivolts to 1.7 volts with 2.5 volt supplies. Okay. But this is a lot of change. This is a ratio of 10 here. Make sense? So there is a simple way of doing something, you know, changing the shape, changing the noise margins. I can change the noise margins by changing W over WN over WP. If NMOS transistor is wider, what's going to happen to the switching threshold? If I widen the NMOS, what happens to the switching threshold? Do they go down? NMOS wider, yeah, it's gonna go down. If PMOS is wider, it's gonna go up. How do you physically, I mean, without looking at the graph, how do you physically explain that? Think about that a little bit. It's a good problem to think of. What's the switching threshold if WP is equal to WN? There will be a point somewhere over here on the graph. Somewhere around 1 volt, a little bit more than 1 volt. Would this yield symmetrical noise margins? No. Where would we like to have VM to be? Somewhere around half the VDD value, then it will be, you know, really symmetrical margins. Where is the half the VDD value? 1.25. Eyeballed to be over here. That corresponds to which value of somewhere around between 3 and 4. So everybody has done inverter layout. So these inverters are going to look a little bit awkward. PMOS transistor, in order to have VTC perfectly symmetrical, has to be much wider than the NMOS. That's not a big deal. I mean, you can lay that out. But you'll find out there are some other negative consequences of making PMOS really big. But you'll find out that this is a relatively forgiving curve. So, I mean, if I choose this ratio to be 2, you know, this is going to be around 1.2 volts. And so it's okay. I mean, what's 15 millivolts between friends? Right? It's relatively forgiving. This is logarithmic. This looks linear. So if I need to logarithmically change, I need to double the sizes in order to linearly change the threshold, the switching threshold. Yes? It is governed somewhat by the mobility ratio. No, it is not really by the mobility ratios. It is primarily governed by, if you look at it, it is governed by the mobilities and VD sats. That's what comes out of this equation. Yes?
Regarding your earlier question, this is what I think. When you make the
Yes, you're essentially right. The wider the NMOS, the conductance of that NMOS transistor has more of a current, right? So it will intersect appropriate PMOS curves earlier. Okay. Sorry for a messy slide. Now, the other thing that I would like to find, let me get a new slide in here. The other things that I would like to find out, what are the exact values of noise margins, if somebody cares. We should be able to tell them how to do that. I found out how this thing looks like. It's not perfectly drawn, I'm sorry. By the way, what happens as I widen NMOS transistor to this curve? You will have it like that. How do you find, for one of these curves, what are the noise margins? I need to find what is V input low and V output low. V input high, right? These are these gain of 1 points. How do you do that? So it looks like I would not be able to get away from what Rachel has suggested to solve this analytically. Find what is the mode of operation over here and solve it analytically. And then differentiate, equate that with -1 and be done with it, right? In order to go about that, what do I need to find out here? So let's try to find what is VIL. What's the mode of operation of the NMOS transistor? NMOS is velocity saturated, or say it's most likely saturated, according to our model, right?
That's sort of like the
starts conducting, just starts conducting down there, down low. And where is PMOS? IDS of NMOS has to be equal to ISD of the PMOS transistor. Right? And I can equate these two things. So NMOS in saturation, K prime, and W over L VGS, which is essentially VGS is VI L minus VT squared has to be equal to K prime P WP over L. And now what do I have here? VSG, that's VDD minus VIL. 1 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / 2 / need to move this to another row. Minus VIL minus VT. And what's happening to VDS? VDS is equal to VDD minus V out. Then I have minus VDD minus, or I'll call this VDD minus V out squared over 2. I'll leave this as V in here. Sorry about that. Yeah, they're VTN and VTP, but that's okay. And then what I need to do from here, solve this as find what is V out as a function of V in, and then find what is dV out over dV in, and make it equal to -1. That's going to give me V in, VIL. I mean, it's not that hard, right? But engineers hate, I mean, typically engineering undergraduates hate to see this amount of work. And it's prone to errors, and you know, I have not, along with negative numbers, my differentiation has been relatively neglected. So we look for simpler things. So, you know, what's the simplest approximation that I can make? Well, here's what we can do and find approximately where the noise margin is. I'll say that instead of having the VTC that looks like that, curved, I'll say, oh, it looks more like this, and I'll find what is the gain at this VM point and find out where it reaches V output high and V output low. It's approximately going to be that. So then V output high minus V output low is equal to minus V output high minus V output low divided by this gain, and this G is the gain. And that is equal to essentially minus VDD over the gain. And then from that, we find what we care about. So what's the gain? Well, here is the gain. I can differentiate this. This is equal to approximately at the maximum point. It's equal to ID at VM times Kn times VD sat n plus Kp VD sat p divided by lambda n minus lambda p. In order to have a finite slope there, you have to have channel length modulation, right? And this is, you know, very solvable from the previous set of equations. Right, I get it from something has gone wild with this. Yeah, so by differentiating this, you can get that. And you can get it. And this is not analytically solved plot. This is showing a plot of V in gain versus V in obtained through SPICE. So you find out that the maximum gain of this inverter happens around the switching point, and it's around 16 in absolute value. And VI low and VI high points correspond to these two voltages where the gain intersects. IL, this is VIH. Okay? And you'll find out that the numbers that you get from this plot versus this approximation that I've shown you, the differences are small because the gain is fairly high. This gain in the center of about 16-ish, 17-ish. Now, with scaling of technology, does this gain get better or worse? Worse. Why? Because it's a function of these lambdas and BD sats. Lambdas get bigger, gains get smaller. Mismatch between lambdas gets bigger as well. Why do lambdas get bigger? Why does that? What is lambda? Lambda is 1 plus VDS minus 1 plus lambda VDS term that modulates the drain current. Why does that get bigger? Because of short channel effects, that it's not only channel length modulation, which also gets worse, but it's compounded by the drain-induced barrier lowering. So this lambda gets really big for modern devices. Okay. By the way, what is a, if anybody has followed any of the device class, Dibble parameter, which is the parameter that tells you when you switch the supply, from threshold of a device measured at low supply at low drain bias versus maximum drain bias. How much should the threshold drop? It's a design parameter for device guys. What do you expect it to drop by? Starting, say, from 400 millivolts, how low will it go due to Dibble? 300. 100 millivolts is their target. They're happy if they can get a device that has a Dibble factor of 100 millivolts per volt. It's a lot. And you can just imagine what it does to your nice curves that used to look almost flat. Yeah, like become nicely tilted, and your lambda gets big. Okay. So, what happens to the gain for what's the gain of these short transistors? It's less than these 17. This was nice old days when we had quarter micron devices. What is it now? Has been dropping, but recently has stabilized somewhere between 5 and 10 for an inverter. Why? Why it doesn't drop down? Can you drop down to 1 and be done with it? No, we do not want it to be 1. But what's the lowest gain of an inverter that we could handle? How bad can things get? Somewhere around there, 5 to 10. Because if it gets worse than that, many things will stop working. And we'll talk a little bit about that, like memory has difficulties. Falling off? Beat on device guys. And they've come up with their tricks, right? They've come up with high K, the electrics. They've figured out how to use the FinFETs and everything else. Don't you have some device people around you near your cubicles? Tell them to do it. Okay, so interesting things happen. So what happens with this gain as we scale the VDD? What is very interesting, it's very robust. It actually gets better as I scale down the VDD. Why is that? And particularly for these short channel devices, it gets significantly better. Why? Did you listen to me what I said 3 minutes ago? Part of it is a component here of longer channel devices, but in particularly short channel devices, your dibble is suppressed at close to fly voltages. You're not exercising the dibble of the device, so it's good. And then eventually, it gets pretty good. But when you drop it to a really low supply voltage, 0.2 volts, the inverter still looks okay. I mean, this is a very robust structure. It's the exact same inverter that works well at 2.5 volts and 0.2 volts. And then eventually the gain gets worse. And when you drop it down to something like 50 millivolts, there is no more gain. No, it is in subthreshold. The whole thing operates in subthreshold. My watch works in subthreshold. Yours too. Well, you don't have one. There are applications that don't have to run very fast, and they can operate in subthreshold. I have not talked about subthreshold models, but it's just showing that this whole thing, just put it in splice, and it's going to run in subthreshold up to some point. What is that magic thing that happens around 50 millivolts where this thing stops working? Well, there is, 20, this is 2 VT. There is some significance of the 2 Einstein voltages where things just don't work anymore. I won't talk about that much. Okay, fair enough. One of the reasons, so here is a simulated VTC. Here is another thing. So here is the impact of sizing, wider PMOS, wider NMOS. We have talked about that. Now, process variations will do approximately the same thing to you. And that is one of these significances of what if a typical gain of a transistor is 5 of an inverter, in a typical process. It's 5. What is the worst case gain going to be? 3, 2, or 1. If it is 1, we don't have a digital gate anymore. Right. That's the impact of variations. And variations are a big thing. Variations have been here forever, but we didn't care too much about them. And, variations, you have a nominal process, and then you can have both NMOS and PMOS transistors slower, both of them faster, or these cross corner points where you have faster NMOS, slower PMOS, and vice versa. It will all affect the shapes here. Yes? Using his argument, that's why I've asked him to come up with this argument. If NMOS conducts more current for the same voltage, it should move the curve to the left. It would intersect these curves in the V. Oh. Okay, I'm sorry. I have what you found out here. It's not bigger. So when you manufacture a wafer or a number of wafers and plot a statistical distribution of VTs, and you're typically going to get some Gaussian distribution. This is going to be typical. This is going to be called threshold turns out to be very high. That's going to be the worst case. That's going to be the slowest devices. That's why we call this a slow corner. And this one, when the threshold turns out to be low, the devices are going to turn out to be the fastest. And we're going to call this the fast corner. And this is engineering lingo, right? When you get a chip, and they'll tell it, it's typical fast or slow. You'll figure that out easily. You power, plug in the supply, flip the switch up, and it's going to run as you have designed for a typical case, or slower or faster. Wow, why don't they make everything faster? I mean, if this can happen, why don't they all the time make things fast? Because that's one of the things. Yeah, it leaks, but you cannot. I mean, you have to center in these things. Just there is distribution of things that because of random effects in the fab and in the devices. Okay, is this clear? And you practice this in the homework, by the way. Do you have any questions about this calculation of the voltage transfer characteristic? Now, I cannot do much more with static characteristics. I need to learn more about the device in order to proceed further. The next thing that we would like to analyze is the delay. Delay is a very important thing. In order to get to the delay, well, I know how to calculate what is, I am pretty sure I know how to calculate what is the equivalent resistance of a transistor, and it's an easy thing. You've done it in the homework. But we need to know the capacitances. So that's what we need to learn. Okay, MOS capacitance. Now, MOS transistor has a lot of capacitances associated with it. And most of them are nonlinear to make things real ugly. That being nonlinear is not that bad. I mean, you can talk to your RF friends and others. They know how to use that sometimes to their advantage. We don't like nonlinear, right? We like linear. It's the same thing as my negative numbers and so on. It's much easier for me to solve linear equations than to deal with nonlinear ones. When you look at a MOS transistor, there are capacitances between the gate and the source, gate and the drain, source and the body, gate and the body, and drain and the body. Every pair of terminals has some capacitance. The only one that I have not drawn here is source to drain capacitance. That capacitance also exists, but it's very small. Right? It's a structure, three-dimensional structure. Between source and the drain, there is a capacitance. It's smaller than the others. That's why we don't draw it. Physically, where do these capacitances come from? Okay, if we look at the gate, here it is. Here is body. Sorry. Body and the body terminal down there. So if I look at this metal oxide semiconductor capacitance against this formed channel, thin channel over here, I know that this capacitance is equal to C oxide. It has some value which is equal to epsilon oxide divided by the thickness of the oxide. That's per unit area. And then, if you want to get it for a particular size of that device, it is equal to W times L times C oxide prime. I know how to calculate the capacitance. I know what is, from my device physics, it's how to calculate this capacitance. But there is one problem. The channel is not a terminal in our model. I know what is the capacitance from the gate to the channel, but in a channel, I don't know where to hook up that channel. So we need to figure out a way how to distribute, how to relate that gate to channel capacitance to some other terminal capacitances, like gate to source, gate to body, and gate to drain. And that's what the most of the art of dealing with the MOS capacitors is. So in the cutoff, what we have is a structure that looks like this. There are no carriers down here to form the other side of the capacitor. You have carriers, a lot of them, distributed down here. And the field lines that originate from here terminate throughout the body of the transistor. Is this capacitance larger or smaller than the capacitance formed between the gate and the channel when the channel is formed? Smaller, because the field lines travel longer. That's all what you need to remember. There is also this depletion capacitance, and if you look at it, depending what you do, if you reversely bias it, you deplete it more, you can make that, modulate that capacitance more. So this total gate to channel capacitance, gate channel body capacitance, because it's a series of two capacitors, is much smaller than this W times L times C oxide. And we're digital people, we'll call it a 0. Now, this depletion region may shrink if you make this gate to source voltage very negative, and this goes back to WL times C oxide in the accumulation. I'll skip that because we usually don't operate these transistors like that. Now, in the linear region, we have this channel formed, and there are carriers here, and this capacitance terminates over there. It is also true that this channel is electrically connected to both source and the drain. So I have this capacitor between the gate and the channel. How do I split it between the source and the drain? Half-half. That's fair. So GS is equal to CGD is equal to 1/2 WL C oxide prime. Sounds fair to me. How would you test if that is a valid split? In SPICE. Or maybe analytically. How would you test if this is a valid split, 50-50? Or let's start with something simpler. AC current is good. Charge. How about charge? Inject some charge and figure out how does it distribute. And you'll find out it distributes evenly. Right, you had this capacitor, and you basically, what did we do? We split it into two halves. One half is here, the other half is here. When we sum them, two capacitors in parallel are equal to CG. Okay, in the saturation region, it's a little bit different. We have lost this electrical contact between the channel and the drain. When I say that, it means that the drain cannot affect the charge in the channel anymore. This capacitance will essentially It's between the gate and the source and not over here. Now you can do this experiment that we have suggested, inject some charge and figure out what happens to the voltage. The bottom line of that, I'm not going to go through that derivation. In 140 we go through that. It turns out to be 2/3 of times W times L times C oxide. And I use this prime over here. Ends up to be 2/3. And this is what I've said. This capacitance that belongs to the gate to drain is essentially 0. Here is what happens to this gate capacitance then versus VGS. So as I'm turning on the transistor, when the transistor is off, when the transistor is off, it is equal to C gate to channel. It is equal to W times L times C oxide. Then, as it turns on, as we are approaching the threshold, we are pushing that charge farther away, and the plates of that capacitor essentially split up further, and then this gate to body capacitance drops down, gate to source and gate to drain capacitance is increased to their value that is equal to W times L times C oxide divided by 2, and in sum they're again equal to W times L times C oxide. Now versus the operating region, what we find out when the transistor is linear, when VDS is approximately equal to 0, then the transistor is the most linear it can be. So this is linear. This total capacitance that is equal to W times L times C oxide is equally split between the two sides. Each one of them gets a half. As you are saturating the transistor, this capacitance ends up being 2/3, drops down to 2/3. All 2/3 are associated with the source. 0 is associated with the drain. Okay. So what's the point here? These are nonlinear capacitances. As I switch the input of a transistor, I'm going to look into a nonlinear capacitor. And that's kind of starting to bother me. We'll have to find out an easy way to do that. There is some good news. There are some capacitances that are linear. There's simply some parallel plate linear capacitors that exist. Typical one is this overlap capacitance. It's between the polysilicon gate and the bulk and the source and the drain areas. We have to have some overlap between the transistor and the source and the drains. Otherwise, it won't turn on. The worst case, it will be misaligned and it will be pretty difficult to turn it on. So there is always some overlap, and this overlap, it's usually given by this drain extension XD, given by the lateral diffusion. You get the parallel plate capacitor size by multiplying that XD with the length of with the width of the transistor. And the capacitors three-dimensionally looking are here. So overall capacitance is equal to Cox times XD. And remember, this is capacitance per linear. Sorry. If Cox is a capacitance per area, CO overlap is per unit width. It's always given per unit width. That's not the only capacitance that exists. It used to be a dominant capacitance, but now the transistors look more like three-dimensional structures. The gates have grown taller. They're very tall compared to the source and drain regions. And you have these fringing fields between the gate and the source and the drain. typical values are easy to remember. They're somewhere around 0.2 femtofarads per micron of length, of width of a transistor. Now, there are other capacitors in the transistor. So we have looked at the gate. We have seen that the gate consists of this nonlinear capacitance between the capacitor between the gate and the channel, and linear capacitors that are in the overlap regions. At the output of a transistor, we have two big diodes, source and drain diodes, that are reversely biased and electrically don't affect the operation much, but there are capacitors associated with the diodes. Do we know how to calculate the diode capacitance? What is it equal to? What is it proportional to? The area, that's pretty good. What else? How about, what's the voltage proportionality? Is it linear? It's a square root in the simplest model that we have learned. And if somebody has tortured you with this, gradient of doping, you'll find out it's a cubic root. In practice, it's going to be something between the square root and the cubic root, and it's going to, the bottom line is nonlinear. Okay. But, that junction capacitance, you can find out. The whole thing consists of the junction capacitance that has the bottom plate. There is a diode on the bottom of this junction and the substrate, and the sidewall capacitance. Along these sidewalls, there are little diodes all the way. So you'll find out that this one, bottom plate capacitance, is defined by per unit area. Sidewalls are given by perimeters. Now, when you calculate the sidewall capacitance, books will typically say that it is equal to the two lengths of the diffusion plus one width of the diffusion. What happened to this other width over here that is sitting under the channel? Why are we not counting on that one? Isn't there a fourth side of a polygon? Hmm? Charged in the channel, but it's a thin layer, right? I mean, this is deeper things down there. So yes, because of that electrical connection, we used to ignore it. But because of a very complex structure, how this drain is being built now, there is some capacitance on that side as well. There is, you have to remember there is something that is called a halo implant, and drain extension and all that forms some capacitive structure down there. There'll be, in modern devices, this would be correct for most of the drain, and then you'll add one more, a little different value for the fourth side. That's the gate edge. Gate times the W. A fourth value, fourth side of that triangle. So this is what corresponds to this, and these three sides are the bottom line is all. This is all nonlinear. So when you're looking at these junction capacitances, this is the voltage versus capacitance versus voltage. It's a C junction as a function of bias. So I'm not going to dive deep into that, but what you find out here is that all of them in SPICE are nonlinear, and as Arko has said, he was correct. It's a junction capacitance divided by 1 plus bias voltage divided by some built-in potential to the power of mj. And this power of mj typically goes from somewhere all these MJ sidewall and so on are somewhere between 0.5, say 0.33 or 0.3, 0.3, and 0.5. They're either square roots or cubic roots or something like that. So we don't like that. What we're going to do in the beginning of the next lecture on Tuesday, I'm going to get rid of that nonlinearity. I'm going to replace it with a linear capacitor, and we are back in business. This is something that we know how to handle. We just have to know the source of the error that will occasionally pop up.